Okay. I owe you something from yesterday. I got so excited about showing you examples that I didn't spend the time to prove the lemma. The lemma that tells us why resolution of singularities in characteristic zero works. So here's the lemma. The lemma says that assume I have an invariant which is a smooth functorial singularity invariant. So singularity invariant, remember, it's a function for each x, for each singular x in y, that in any y that takes values in an upper semi-continuous, in a well-ordered set, which is upper semi-continuous, and which detects singularity. Smooth means that the maximum locus is smooth, and factorial means that it's compatible with smooth maps. So in particular, localization, open sets, etc. Assume I have such an invariant. I assume I have a center, something I can blow up, as we discussed last time, for a particular x inside y, and assume two conditions, and that's all you need. One condition is that the support of this center is precisely that maximum locus, which by assumption is smooth, but the support of a center is always smooth. It's a vanishing locus of a partial system of parameters. But assume that it equals the maximum locus of the invariant, so they speak to each other. And moreover, and this is a bit more subtle, the maximum invariant for x is the same as the maximum invariant for bx, which is the deformation to the normal cone of x inside the deformation to the normal of z in x inside the deformation normal cone of z in y. So I forgot to write what x is. X is this, and this is the normal cone of z in y, and this is z in x, and maybe I should write y there. Okay, and the proof of this lemma is completely geometric. So being geometric, I can just stand at the picture and wave hands, and you'll know that it's true. Okay? So, first claim. So say W is the maximum locus of Bx, of the invariant on Bx. And the claim is that W equals the vertex. Okay? That's a claim. And so let's see, and that has to follow from what I require of an invariant. It should be completely mindless. Okay, so let's see how it works. First, I know by assumption 1 is that the maximum locus of the invariant of x is z. Right? So if I just look at this slice, the maximum locus is z. But the invariant is factorial. So and if I ignore s equals 0, then this is just a product with GM, with C star. Okay? Product with C star is a smooth map. So this means that this is equal to the maximum. I'll write Bx0, the part that does not include s equals 0. Maybe I should call it Bx not equal to 0. Okay? Because I just take a product with C star, and I assume that my invariant is compatible with any smooth map, in particular product with C star. Okay, so this means in this locus, this is the maximum locus of the invariant. And also, I know that a singularity invariant being upper semi-continuous, the maximum locus is closed. So this means that W includes V as a component. Because W includes V, that's the maximum invariant is the maximum invariant of X, so W includes V, and there might be something here. And all I need to show is that there's nothing here on the normal cone. Okay, so suppose B is in the normal cone. So here's B. And the invariant of B equals the maximum invariant. Okay? Now the invariant is functorial, and I have a group action here. So if it's functorial, then it's the same along the entire orbit of the group. It's the same as invariant of TB for any T in C star. Okay? But the invariant is upper semi-continuous, so the invariant here, B0, the limit of the orbit as T goes to 0, can only go up, but it has no place to go up because this is a maximum invariant. So the invariant here equals the invariant here. So if B is not already here, this means that I have another component of W passing through B0. But I assume that it's a smooth invariant. The maximum locus is smooth. Okay? So W contains V as a component. Smoothness means that it has to be a connected component. And I just got a contradiction if B is not in V. So this means B is in V. So this is impossible. This is the only possible B. So the maximum locus of the invariant is V. All right, so with this claim, I'm saying the lemma follows. Why is that? So the maximum invariant is obtained in V only. So this means that if I remove V, the invariant drops. So Bx plus is the part that I get when I remove V. Right? Jarek, you seem to be confused. How you know this? Okay. So I got this. But what do I know? I know that the blow up, so I have Bx plus maps to the blow up. And this map is just a group quotient. It's a quotient by C star. So it's a smooth map. It's a smooth map. So this means that this is equal to the maximal invariant of the blow up. Which is what I wanted. So I use some hand waving, geometry, not even differential geometry, no calculus yet. And the assumptions and the lemma follows. And the lemma says, if these assumptions hold, then I have resolution of singularity. This is the corollary. Then the invariant drops. And the corollary says that if these assumptions hold whenever I have an x in y, then I have resolution of singularities. Okay, stop me here. If this is all you get from the lecture series, I've done my job. So now you know what you need to do in order to resolve singularities. You need to prove this theorem. So I just copied the lemma, but saying that, I studied it slightly differently in yesterday, but okay. So the theorem that we prove, and in essence also McQuillan, we didn't write it this way, and he didn't write it this way, but the theorem is there exists a smooth functorial invariant. For any x in y, there's a center, J bar, such that the support of the center is the maximum locus and this second condition. So the center and the invariant need to speak to each other to be intimate in two ways. The support of the center is the maximum locus, and the invariant does not grow when you go to the deformation to the normal cone. And I showed you that if in a non-example yesterday, that if you choose the wrong center, the second half will not work. So you have to carefully tune the invariant and the center to speak to each other. And the rest of today is giving you ideas how this is proven. So let's start. Yes. Yes. So the center is actually functorial as well. I'm not stating the strongest possible statements because I want to explain how things work and not write a paper in front of you. Okay. So in order to prove this, you need to do some calculus. Okay? So need derivatives. So there's an algebra step that I'm skipping. Instead of looking at the subright, I'll look at its ideal. So I'll work with ideals now. And there's a similar statement for ideals that I'll allude. And I'll define the derivative ideal of I to be, I'll put an A here. So I take all possible differential operators. What did I lose? I lost my name tag. All differential operators of order at most A, and apply them to all elements of the ideal, I get an ideal. Note, I'm working in characteristic 0, which implies that D less than or equal to A, I is D less than or equal to 1 of D less than or equal to A minus 1 of I. Okay? That's because of how derivatives work in characteristic 0. Integers are invertible in characteristic 0. So you can, okay, so next, I'll define the, here's an example. So to take derivatives, if I need x, I need yz, I mean 2yz, but in characteristic 0 I can divide. And I need y squared, and that's the derivative ideal of this. The original, I should take also, so in this formalism, I don't need the less than equal. I can take just the, yeah. So now let's define the next thing, order. What's the order? The order of an ideal at a point. I'll give you two definitions. This is the maximum integer a such that m to the a contains the ideal. But thinking about Taylor expansions, this is the same as the minimum of a such that the eighth derivative of I at p is contains a unit. right? So this is the order of vanishing of an ideal at a point. This is the first approximation of a singularity invariant. It's functorial, it's, okay, so note, so it's functorial because of compatibility of derivatives with smooth maps. It's also upper semi-continuous because the order is bigger or equal to A if and only if P is in the vanishing locus of the A minus 1 of I. So order is upper semi-continuous. This is, if the bigger equal locus is closed, then it's upper semi-continuous. Okay? And as I said, also functorial. It's not a singularity invariant because it does not detect singularities. So the order at 0, 0, 0 of the ideal y squared minus x cubed z is 1, but this is clearly a singular curve. So it's not enough. The order is not enough, but it's a beginning. So what do I do next? Next, I define for you. Here we go. I'll make an assumption. Assume the order is A. And then I'll say, so a definition, X in OP is maximal contact for the ideal I if X is an element in the A minus 1 of I and some derivative of X is a unit. So, so it's a parameter. I mean, I don't want X itself to be a unit. Here's a lemma. In characteristic 0, a maximal contact exists. And why is that? That's because the order is, because the order is A, I have something here whose first derivative is a unit. I can rescale it so that the first derivative is 1. So, for instance, the order at 0, 0, 0 of x squared plus y squared z equals okay, so what is the order of vanishing of this at the origin? It's 2, okay. So I need to find an element in the previous derivative, which is a regular parameter, which has a, okay, so x or x plus yz, either one of them is a maximal contact. Questions so far? Yeah, yeah. x plus y is not a maximal contact, because x plus y is not an element of that ideal. So it's important. So this is a key difference from characteristic P. This doesn't work, but you want a replacement for maximal contact in characteristic P. And I guess Olivier would know that what you have to take is a variable that detects the characteristic polyhedron. So in Hironaka did not have, in the original paper, he did not have maximal contact, and what he had is this. So he had these diagrams, and so something that detects the characteristic polyhedron, it's a later language, is the good replacement for maximal contact. So that's the first difference. Okay, so here is another thing I want you to note about this notion. If x is a maximal if x is in the a minus 1 of I, then the vanishing locus of x contains the vanishing locus of the a minus 1 of ai, which is the points of the order a locus. Or order at least a locus. So since maximal order is a, so this means that if you still think about order as a first approximation for a singularity invariant, a maximal contact element is a good candidate to work with inductively because it contains the worst locus of your ideal. It contains the locus where the order is at least A. So maybe I should draw a picture here. On this picture, which color has not been used? Red, luckily, has not been used. So here's I'll call this H, which is vanishing locus of little x, a maximal contact hypersurface. It's something that contains the locus of order A, and as we'll see, in particular, it contains the locus Z of that we'll define. Okay, so the vanishing locus I'll have to, V of x is H is a good candidate for inductively replacing the ambient space Y. I also need a good candidate to replace x itself, or at least the ideal of x. So what? Okay, so now I can move this all the way up. No, I'll move it here. I'll move this all the way up. And while the last board is going down, you get to ask your questions about what I've done so far. So I've identified for you a hypersurface on which I will restrict things. The worst locus, in a crude sense, already in the crude sense of order, is included in that hypersurface. And one thing I forgot to do is start my clock, so I have to set it up. So you still can ask questions. So I want 25 minutes now. So I have a 10-minute warning. I guess I'm very clear, so I'll rush on. Okay? Right, so the next thing, so now this is already here. So I can erase this. Now I want to define for you what replaces x, the singular subvariety or the ideal of x, I. And this is where this will bring home the reason why I use ideals. It's a classical idea that everybody has used. It's particularly present in the work of Villamayor and collaborators. That you do something with ideals. And so what I want is to define, so I define for you di. And I'm interested, the next derivative is going to be the unit ideal at the point P I'm looking at. So and I also have the ideal itself. The order of vanishing of I is A. The order of vanishing of the first derivative is A minus 1, all the way to the order of vanishing here, which is 1. The order of vanishing of the next one is 0, because it's the unit ideal. So the correct thing to use, and I'll explain this in a minute, is all of these ideals. I want to restrict all of these ideals with their respective orders to the vanishing locus of x. So I'll call, this is I0, I1. I'm counting the number of derivatives I'm taking. No, no, I'll count the number between. Yeah. So need to restrict all these I, J restricted to the vanishing locus of x, to what I called H, the vanishing locus of x. So Villamayor and collaborators introduced Riesz algebras as the way to do this. And we also adopt this in at least one of our papers. But the classical approach is to just bundle them together in a new ideal that retains all this information. So there's I'll define a coefficient ideal. Is the ideal which takes into account all of these with their respective orders. So I take all possible monomials so each one of these comes with its respective weight, and I take monomials of weight at least a factorial, because that's I mean, I could do less than that, but that's certainly a degree where I can guarantee that everything will appear. So if I know that this behaves well, then I know that all of these behave well with respect to their respective orders. Okay, so this is just a way to bundle together all of these. So this has order a factorial, which is a minus 1 factorial times a. So there's a rescaling factor of a minus 1 factorial that I have to take into account if I use this formalism. Okay? I'll also introduce the restriction of this. I mostly need this So the restriction of this to the vanishing locus of H is the ideal I will consider on the vanishing locus of X. So this is the ideal shorthand for this, and the ideal that retains all the relevant information, as I will explain as we come. But for now, what I want to do what I want to do is I want to define the center. I'll define the invariant and the center for you. Now I have all that I need to define the invariant and the center. And that space is not enough, so I didn't, so the coefficient idea of this, A is 2, is, if you think about it, it's x squared y squared z y to the 4. These are examples and also exercises. It's not an accident that EX stands for both. You have exercises in your notes, and certainly if you're a PhD student, I would suggest doing the exercises. If you're not, you're on your own. Okay, so I want to define the invariant of an ideal at a point P, and it will start with A1. A1 is the order. And I choose the maximal contact. There's a choice involved here. And the center I'll call X, X1, because there will be other X's. Okay, and I need to tell you how to continue. Well, I told you which ideal to take. So let's say I already have things defined recursively in one dimension lower. In particular, the invariant of I of X is already defined because it's one dimension lower. H is one dimension lower. And I assume that it's B1 through Bk. And remember that this is rescaled by a factor of A minus 1 factorial. So I'll define AI to be Bi divided by A1 minus 1 factorial, so to scale back. If this is the invariant, then the center of I of X is of the form x2 to the b2 all the way. So this is b2 to xk to the bk. I deliberately start this invariant with 2 so that it fits in the recursion. Except that these are variables on H, so I'll call them xi bar, and I'll choose xi such that xi mod x1 is xi bar. So I choose lifts. So now I can write, I define for you a2 through ak, and I define for you x2 through xk. And here's the invariant and center. And the claim is that this satisfies the theorem. The claim is that this satisfies the theorem. Now you can sit down and compute. Okay, time is short, but if I have time, you choose something from the beautiful pictures and we can do it. Or we can just do the Whitney umbrella. Of course, I need to tell you how this is ordered. This is ordered lexicographically. And so it stops at some k because at some point the ideal might vanish identically. And then you can think of it as if the other variables come with weight infinity. So that's how you order. So 2 is bigger than 2, 3, because 2 is like 2 comma infinity, if you wish. So that's a lexicographic order. It is a well-ordered set because even though there are denominators, the denominators are bounded by the previous terms, so it's order equivalent to sequences of integers of length at most the dimension of y. So what do I need to show? I need to show that the invariant is a smooth factorial invariant and that its support is the maximum locus. So its maximum locus is the support of J. And then I need to also prove part 2. So there are parts of this that are almost immediate. Okay? Okay. So this is the definition of the invariant and center. All right. Right, so there's an issue of in what sense is J unique? And I'll say in what sense it is unique, but so remember, J is not a sequence of variables with powers. It's a monomial valuation. So in that sense, it is unique. So since you ask now, I'll tell you why the lifts of the xi are immaterial. That's the easy part of independence. Oops, I went too far. Why does it not allow me to go 2 at a time? I don't know. Okay, I want this, don't let me erase this board. So remember that the order is upper semi-continuous. I think this might have already been erased. So I want to say that the invariant is, claim the invariant is upper semi-continuous. So to prove this, first note that the order A1 is upper semi-continuous. And also note that its maximum locus is contained in the vanishing locus of x1. So I might as well look at H. And inductively, B2 through BK, and therefore A2 through AK is upper semi-continuous. So this together says that the invariant, lexicographically ordered, is upper semi-continuous. But this same argument gives me more. So functoriality, again, is so functorial A1, which is the order, is functorial for smooth map. And if up to the choice of x1, so once I choose x1, the rest is inductively functorial. So I'm shoving under the carpet the choice of x1. Incidentally, I was going to show you why the choice of x2 through xk is immaterial. So if I replace x2 by x2 plus some multiple of x1, or any of the others, then you note that the valuation, so the valuation of x2 plus alpha x1 is, okay, so the valuation of x2 is 1 over, I write, the valuation of x2 is 1 over a2. The valuation of x1 is 1 over a1. And I multiply it by something is, but a1 is smaller than a2, then 1 over a1 is bigger than 1 over a2, or smaller or equal, and therefore the valuation of this is bigger or equal to 1 over a2. So the valuation of this is still 1 over a2 because of the non-Archimedean property of valuations. Okay? So the lifts don't matter. I'm not sure I will say anything about why the choice of x1 is immaterial, but it is also true. Okay, so I'm going to say also that the smoothness, and at the same time the center is supported in the maximum locus, this follows inductively. So the maximum locus of the invariant is included by the fact that it starts with the order included in the vanishing locus of x1, and inductively is inside the vanishing locus of x1 is the vanishing locus of x2 bar through xk bar. So together the maximum locus is the vanishing locus of x1 through xk, which is smooth. So I sort of got factorial up to x1. It is a singularity. Well, okay. It is smooth. That I got. And the end part one, the support, is the maximum locus of the invariant. Okay? So the only thing that is left to prove for the theorem is this. And by the non-example that I gave you yesterday, you know that this can't be a triviality. You have to do something. Okay, so I'll pause now and ask for questions. Okay, so I think I want the middle board all the way up, because that's the one I don't want to erase. And I want to send this to the middle and to, oops. I want to send this to the middle and deliver this one all the way down. Okay, so now I'll just work with these two and don't need to switch too many times. Oh, so I'm erasing. So remember, in order to understand, so the coefficient ideal is here in order to replace all the derivatives of the original ideal up to the a minus first derivative. So if I okay, so a few words about admissibility. So remember that the center is a monomial valuation, so the Vj of x1 to the I1 of a monomial xk to the, let's do a general, summation ci x to the ik is the minimum over ci. This is not ideal, this is an index set. Of ij over aj. A sum ij. So that's the definition. So what I wrote here is the value of this monomial, and I take the minimum of those monomials that appear. So this is how monomial valuations work. You choose a sequence of parameters. So it might as well work in the completion, and there's a question.
I was wondering how these weights of previous vector relate to 1 over AI. So we have this WI.
Right, so remember, so the way I did this is I took A1 through AK, and I said this is, I rescale it to be so this is L times 1 over W1 through 1 over WK, where WI are integers. 10 minutes to go. So this is the way they are related. So the L, oops. If you have chalk in your hands, this won't work. So in particular, the Vj bar of f is L times Vj of f, because you replace Aj by Aj over L, so you look at summation Ij times Wj. Did I answer your question? I agree. So I say that, okay, so claim with this center, if f is in I, then the evaluation with respect to j of f, not j bar, is at least 1. And this is an outcome of Taylor expansion, right? So f, you expand, f is summation ci x1 to the I. I just expand in terms of x1 and ci functions in the other variables. And the ci are, by definition, d x1 of f to the di, dx1 to the I of f divided by I factorial. So the I factorial doesn't matter. So this is at 0, x1 equals 0. In other words, these are in the ideals that I erased, the ideal II restricted to the vanishing locus of x1, right? So maybe I should write this. So this is C0. C0 is in the restriction of the original ideal plus C1I. C1 is in the first derivative. In the first derivative, sorry, x1. So this is in IA, this is in IA minus 1. So everything here appears in its correct weight. So if f, so right, so I expand f, the weight of everything here. So x1 is of weight 1 over a1, and things in this derivative ideal are in weight at least 1 over, is the complement 1 minus 1 over a1, this 1 over a1, and together it's in at least weight 1, etc. So just Taylor expansion. So this is somehow the way we come up with such a thing. Just with Taylor expansion, you realize that this center has a property that the evaluation of every element of the ideal is at least 1. And if you can rescale, so the evaluation, so if I take the derivative f in the derivative ideal, then the evaluation of j of f is at least 1 minus 1 over a1. That's because if you take the derivative with respect to a1 to x1, that's what you drop. And if you take a derivative with respect to something else, you drop only 1 over aj, which is a smaller number. So this holds. And similarly, f in the coefficient ideal implies that the evaluation j of f is at least what? A1 minus 1 factorial. So everything appears in its correct evaluation. So this is our definition of saying that J is admissible. We say J is admissible for I J is admissible for I if every element of I has valuation at least 1. And I just argued that this holds. And here's a proposition that says in which sense the center is unique, and tells you that x1 does not matter, except that I will not prove this proposition. I only have 3 hours of lectures, not 5. So proposition, which can be taken as an alternative way to define the invariant and the center, anything that I say today is in the paper with Temkin and Wlodarczyk on weighted blocks. Proposition J is the unique center of maximal invariant, which is admissible for I. So this tells you that it's unique, and it in particular says that the choice of x1 doesn't matter, and therefore functoriality in particular works because you might as well choose x1. So what does admissibility tell you? It tells you how to transform elements of ideals. So if the valuation of J of F is at least C, so this is equivalent to saying that the valuation with respect to J bar of F is at least L times C. L is this rescaling factor of from J to J bar. So this tells you something about what happens when you look at, so I have to involve B at some point. So if I have B mapping to Y being the map sigma, the transform sigma, then the valuation with respect to J of F is at least C if and all implies that sigma upper star F is S to the power, S is the exceptional variable, remember, S to the power L times C times some other function in the transformed variables. So the number of times you can pull out the exceptional from the pullback of the function is given by L times the valuation of the function. How do you see this? You just plug in xi equals s to the wi xi prime and calculate the valuation. So this is just a computation of valuations. So you write f summation ci x1. This just says 1 minute. And you plug in and you get that summation ji over ai bigger or equal to c implies that ijwj is bigger or equal to L times C. And so this is the number of times that you get the S out. You have a similar rule for derivatives. And to cut a long story short, there's a quick, there's a lemma that says that this transform is compatible with taking derivatives. And which means in particular that you might as well replace the ideal by its coefficient ideal. And okay, so what is remaining? So okay, my time is up for today. I'll maybe spend a few minutes. It's not tomorrow, it's on Thursday on the rest. But just to tell you what it's about, to show that the maximum invariant here is the maximum invariant on X, I actually show that the center of Bx is obtained. So the center J. Oh, where is the center? Is given by x1 to the a1 through xk to the. So the center on Bx is just replacing the xi by xi prime. In particular, x1 prime is a maximal. The order is a1. x1 prime is maximal contact. And this is the center. In particular, the invariant is a1 through ak. And that's that with. So I'll spend 5 minutes next time just finishing this up. I'm sorry, this is a little bit of a cliffhanger now, but maybe people will come next time because of this.
Thank you.